Let's do a quick review of the major equations that we've encountered so far for our study of things that translate. That is, study of objects that move from point A to point B in space. So we began this semester with a study of kinematics, and there are 4 kinematics equations that you've probably committed to memory by now. One of them says final velocity is initial velocity plus acceleration times time. Final velocity squared is initial velocity squared plus 2 times acceleration times displacement. Displacement is equal to initial velocity times time plus 1/2 acceleration times time squared, and displacement is equal to 1/2 initial velocity plus final velocity multiplied by time. From there, we moved on to a study of Newton's laws. The main equation was the sum of all external force as a vector quantity is equal to mass times acceleration. After our study of Newton's laws, we went on to a study of work and energy. Said kinetic energy, for translation, is 1/2 mass times velocity squared, and work is equal to the integral of a force vector dot product with incremental displacement, which led us to a study of impulse and momentum. We defined impulse as a vector quantity that's equal to force multiplied by time, and impulse is also a vector quantity that's equal to mass multiplied by velocity, and in fact the impulse acting on an object is equal to the object's change in momentum. And we also restated Newton's second law of motion, that the sum of all external force is the rate of change, the time rate of change, the derivative with respect to time of impulse. Okay, so all of these equations have an equivalent or analogous expression when it comes to objects that rotate. So the kinematics for objects that rotate, final angular speed equals initial angular speed plus angular acceleration times time. Final angular speed squared is initial angular speed squared plus 2 times angular acceleration times time. Angular displacement is initial angular speed multiplied by time plus 1/2 angular acceleration times time squared. And angular displacement is 1/2 initial angular speed plus final angular speed multiplied by time. Here's something new that applies to this unit we're beginning on rotational dynamics. It says the sum of all external torque, which is a vector quantity acting on an object, is equal to the object's rotational inertia multiplied by its angular acceleration. There will be much emphasis given to this equation in our new unit of study. Rotational kinetic energy is equal to 1/2 times rotational inertia times angular speed squared. And work can also be found by taking an integral of the dot product of a torque vector with incremental angular displacement. And lastly, we'll say that the net external torque acting on an object is the time rate of change of the angular momentum for an object, where angular momentum is defined as either a rotational inertia times angular speed, or angular momentum is the cross product between lever arm and linear momentum. So we see this equation is analogous to this equation, and this equation is analogous to this equation. Suppose we should make one more analogous equation. Another way of saying impulse is change in momentum is to say force multiplied by time is equal to mass multiplied by a change in velocity. So likewise, we can say that a torque multiplied by some amount of time is equal to rotational inertia multiplied by a change in angular speed. So as a preview of things to come in this unit of study, there are 1, we'll say 2a, 2b, and 2c. In other words, our main emphasis is on torque and angular momentum. So in the next video, we'll define torque and provide a few examples.